one of the Accuracy Masterclass series presentation, and we're going to talk about feature selection today. So basically, what I'm going to do, I'm going to run some give you a small overview of the topic, introduce you to different methods of feature selections, and make a summary and share my thoughts on this. So what is feature selection basically in general? I like to think about feature selection as a technique for dimensionality reduction. And why this is important to reduce the dimensionality of your data? Well, basically, even from a simple point of data engineering perspective, right? You can actually simplify your data pipeline, because nowadays, if you pre-select some specific features for your model, you don't have to transfer all the data. You can transfer like a particular features from a different table. So that's one of the points. Well, obviously, you don't have to store unused data, basically unused feature for your model, because that means you can reduce the storage space. Of course, it has something to do with curve of dimensionality, because the less dimensions you have, the better, basically, in general, especially for unsupervised techniques, like clustering, for example. From the other hand, feature selection for clustering is a completely different beast. We're not going to cover this in our current presentation. And the last but not least, interpretation of your models. Even a simple linear model is way much easier to interpret than you have, let's say, 4 features than you have, let's say, 1,000. So that is something quite important to have in mind as well. So how we can reduce our dimensionality? We basically have 2 techniques, like in general, of course, like it's one of the way to classify it. You can use a feature selection, or you can do a feature extraction. What's the difference? Well, feature selection allows you to pick up a subset of the features you have. At the same time, feature extraction basically creates a new feature representation for you. So feature extraction, nice example can be PCA, for example, or t-SNE visualization of multidimensional data into 2D space. So you still require all features to be present. You just use them, put them into some sort of a function, which actually, gives you a nice new representation ideally in a smaller space. While feature selection actually tells you like what features are useful, and you can completely remove the unuseful features. We're going to cover feature selection on this topic only. We're not going to talk about feature extraction. So there is a different way to classify a type of feature selection. One of the ways is basically, you can split them up by how they use target variable or not. So like a supervised, unsupervised methods. That's not my preferable way to classify them. I usually try to classify them using the way basically the way they basically designed. So, and we can actually I would highlight 3 different groups of feature selection methods. It's a filter, embedment, and wrapper. So, and filter is quite simple. It's one of the simplest methods in the whole family. An idea is of all filter methods is quite simple. It's very generic. You just basically assign some score to the feature, and based on that score, you can actually, threshold and remove features which actually below the threshold, or you can rank them and take the top 5 or top 10 or top n, basically. So what kind of scores you can assign? Well, simple way gonna be, let's say you can measure the variance of the variable, and based on that, you can remove features that have a low variance. You can use you can measure the correlation between the features in your data set and use pairwise correlation to remove features that's actually highly correlated to each other. Or you can run different univariate analysis between the feature and the target, and measure how feature basically is good in predicting the target in some sense. So as I mentioned, variance threshold is quite simple, right? You basically, what you need to do, you just need to measure the variance. And idea behind it are features which has a bigger variance, contain more information, and might be more useful, which is not always the case, of course. It's assumption. And as always, in machine learning, you have to know the assumptions behind the methods you're going to use. It's the truth for anything, like machine learning models, validation schema you use. We all operate under some specific assumptions, and sometimes this assumption does not hold. So there's a pretty strong assumption actually to say, variation can be quite important. So what's good about these variance threshold methods? Well, it's very fast. You just need to run it n times, where n is the number of features you have in your data set. Features, linear time, good, fairly simple way to measure it. Okay. What's bad about it? Well, there is no way you can count the interaction between features, right? You just measure a single feature all the time, and you don't take the relationship between target and the feature into account. So basically, you just analyze feature by itself, without any connection to the specific data set or specific target or specific problem you have in mind. Why it still might be useful? It's, as a simple example, it actually allows you to remove constant features from your data set, because sometimes if you take a subset of the data set, you might end up having a constant for particular values, right? For particular features in your data set. And there is no reason to keep them, because any machine learning model will basically ignore it, like for sure. So constants definitely can be removed. And if you just put a threshold of 0 to the variance threshold, that means the variance is going to be 0, and that's true only for constants. That's a simple example. Basically, I try to provide a code snippets for all techniques I described today. So, and basically, right, again, like for example, in this particular case, I know for sure what an MNIST data set, which contains handwritten digits from 0 to 9, there is a lot of black pixels, and they can potentially be removed out of the data set. Although it's not the best way to model to model this particular problem using tabular representation, but it's still a nice example. What's also important about variance threshold? Well, it's actually scale dependent, right? So you have to make sure the features in your data set are on the same scale, let's say from 0 to 1 or from -1 to 1. In that case, you can actually put all your features to the same transformer and assign the same variance threshold. If your features contain different scales, and you don't want to scale them, let's say, to transform them basically to the same scale, well, you have to analyze them separately in that case. So the next technique in filter methods, it's a univariate analysis. And in a simple words, it's basically, is measurement of how good is a single feature in predicting target, right? You can run different statistical techniques to find that. There is a whole family of such kind of tests. An idea is, again, you basically measure the target, but now in this time you measure the target against feature against the target you have. So what's good about it? Well, now basically you're selecting features not just by themselves, but actually in relation to the target you have. That means you measure the feature goodness in relation to the problem you're trying to solve. Again, it's fast, right? Again, you don't take a relationship between features into the account. That's going to be a major minus of using this technique, because sometimes the feature interactions might matter. Maybe not like a high-level interactions, but let's say you have two features, they can actually go together. Let's say day of the week, for example, right? And let's say time of the day. In that case, you can actually extract additional seasonality in your data points. Also, univariate analysis in general case, as a lot of statistical tests, they actually assume linear dependency between the feature and the target. And that means if you have a nonlinear, and especially a nonlinear, non-monotonic relationship between the feature and the target, this test might be not able to catch it up. Just something to keep in mind. So that's one of the examples how it can be used. And there is plenty of different examples in scikit-learn library basically. So what you can do in this particular case, we just download the dataset. We scale the dataset because for statistics I'm going to use, which is a chi-square, I need to have a non-negative values. I know for sure what MNIST data actually varies from 0 to 255, but to make this example actually complete, I decided to scale it as well, which is actually not necessary for this particular data set. So, and what I do, I basically select k best features out of the data set based on the relation to the target, based on the chi-squared statistics. That's it. Feature pairwise correlation. So what you do basically, you measure the, the feature in, let's say, connection. In this particular example, you measure basically a correlation, how two features actually correlated to each other in your data set. Why this is important actually? This is important because a lot of machine learning algorithms actually very sensitive to multicollinearity in your data set. That means if you have features which are really highly correlated to each other in the data set, that might actually hurt your model. In some cases, quite significantly. So this is something that usually a good idea to do. Unfortunately, in some examples from life science, it can be really, really slow and it's really, really hard to do. Like, for example, if you have a human DNA methylation data set, it contains like 500,000 of columns, and you would like to, that means if you would like to, straightforwardly measure the correlation and build a correlation matrix, you will end up like having a matrix with like a 0.5 million rows versus 0.5 million columns. That's a huge matrix, actually. I'm not even sure you're able to fit it into RAM. So, and it takes quite a while to calculate. Again, if you measure a correlation, you always have to be aware of what exactly you measure, how exactly you measure the, dependency of two variables. In case of correlation, you have to be sure, you have to acknowledge the fact that actually it measures the linear dependency. Again, if you have non-linear dependency, maybe measuring correlation is not a very good idea, but it's kind of fast, right? Why we usually selecting these type of statistics tests and this type of measurements, because they are quite fast. Obviously, you can try to measure non-linear dependency by fitting a model, or maybe like, like let's say, like for example, non-linear model to the trying to predict one feature based on another feature, but that's definitely going to take way much more time to compute. So that's a code snippet how basically to perform it. I was not able to find any library which does it by itself. So it's basically I implemented myself in a quite straightforward way. So what we're doing here, we calculate a correlation matrix, and because we don't care about the sign, the sign of correlation, we just need to measure how strong correlation is. We just take an absolute value in that case. Again, correlation matrix is a symmetric matrix, so we don't need actually the bottom part of the correlation matrix at all. So I remove it, and after that, I basically find columns which actually has a correlation more than 0.95, and that's a columns I'm going to drop from the data set. So yeah, that's basically the code example. All right. The next family of methods is going to be embedded methods. And the basic idea is quite simple, right? There is some algorithms in machine learning space and approaches that actually kind of do feature selection as a part of a training process. A good example may be a decision tree. If you, let's say, if you have a shallow decision tree, like, with a depth of 2 or 3, it's going to be forced it's going to be forced to pick up only 2 or 3 features, right, which is the most important from a data set. Even if your data set contains thousands of features, if you hit a single decision tree, which has a small depth, you won't be able to use all the features available. You have to pick up some of them. So what also we can actually use? Well, one of the simplest, straightforward, and quite practically useful approach is just use a L1 regularization for your linear model. So what's so special about L1 regularization? It actually, so what you do, you basically punish your model for having high absolute values and U weights of your linear regression or logistic regression model. That means the model is actually forced to reduce its penalty by reducing the weights up to 0, basically. and to have zero coefficients, it actually forced to create a quite sparse model. So you have, let's say you have like 1,000 of features, you might end up actually having a lot of zeros in your coefficients and have like some only meaningful features will have a non-zero coefficients at all. So again, because we have a regularization term, which actually straightforwardly punish for big weights, you have to be sure your features are on the same scale. That's one of the biggest reasons why you use all these pre-processing step in scikit-learn. It's a regularization in in linear models. They have to be on the same scale. So what's good about this approach? It's kind of fast. It takes all the features at once. It's relatively cheap. Again, if your data set contains highly correlated features, in case of L1 regularization, you might the model might end up picking up one of the features all the time, or actually can split the weights between the feature. It depends on the alpha parameter of your regularization technique. So, but basically you would not have, and actually in some cases, if you run it on a cross-validation fashion, you'll be able to see that if let's say you have two highly correlated features in your data set, you might end up switching the weights between them for different faults in your cross-validation. In one fault, this is going to be zero, and this is going to be, have some weight. In next fault, it's going to be vice versa. So it's going to be, it definitely doesn't help your feature importance analysis at the end of it. So you have to make sure you don't have a highly correlated features in your data set. Otherwise, this technique might return some confusing results, especially for highly correlated features. So again, quite simple, straightforward example. We do need to scale our features first. As we create a Lasso model from scikit-learn, that's our parameter alpha. If we increase it, we will end up having less features with zero, less feature with a weight of zero in the model, with non-zero weight, sorry. So the biggest value of alpha, the small amount of feature will have non-zero coefficient. The smaller value of alpha will get you more features with non-zero coefficients. And basically what you need to do after the model fit, you just need to analyze the coefficients, right? And pick up all features which has a non-zero coefficients, and that's going to be pre-selected features from the data set. Again, one of the biggest downfall on this approach is going to be you assume linear dependency. Because it's a linear model, you can't go beyond that. Like if you have like features which has like funky non-linear dependency with a target, it might end up being dropped from the data set. Okay, what else can be done? Well, random forest, right? Actually can give us a feature importance at the end. So we're gonna use that. That's like actually a good idea, especially because in scikit-learn nowadays, they're using impurity-based feature importance. And idea is quite simple. So basically on each split, you measure how your impurity decrease basically, right? So assuming that, feature, the best feature will gonna improve your score significantly, right? You also have to wait by number of examples which end up in the leaf, right? Because, let's say if you greatly improve your impurity score, but you end up with a two values in the leaf, it's maybe not statistically significant, so you have to reweight it. And basically, that's how you calculate the feature importance for the data set. Now you can actually extract it from a random forest, pick up the top 10 features, for example, and yeah, that's end up your feature selection process. So what's good about this approach? Well, it's able to capture nonlinear dependencies, which is good. Yeah. If you have, guess what, highly correlated features in your data set, they're going to share the importance. So basically the importance will going to be split between this feature, almost equally in some cases. It depends. If your features, let's say correlation coefficients is 1, it's going to be end up, using 1 or another in every single tree, and the feature importance is going to be evenly split between them. So if you have a high cardinality categorical column and high cardinality means you have a lot of unique values in your categorical column, and you one-hot encode it, the feature importance for, let's say, for the column in general, going to be kind of inflated, because, you know, every single, especially 0, one-hot encoded features is going to be not very helpful for the model in general. So that's yeah, that's going to be one of the a trick here, how to present the categorical feature in your data set, so you can actually measure the importance of this feature and actually model using this feature efficiently. But unfortunately, that's a question for another talk. So fairly straightforward. Again, we just fit the model, and because it's a random forest, we actually don't care about the same scale of the features. It's random forest. One of the beauty of these tree-based algorithms, you don't have to make sure you have the same scale of features. It doesn't matter for random forest. Very good. Fit the model, get the feature importance, sort them based on the importance score, and pick up the top 10. That's how you pick up features. You also can run a threshold, right? But you cannot do it automatically, because basically, if we go, can I go? Yeah. So basically, you reweight your importance, so the sum is going to be end up to 1, and that means your threshold going to be always depends on how many features you have, basically, right? So you have to, if you want to use a threshold, you have to basically, you know, plot. You have to print the table of your features to understand, you know, how your basically feature importance score is actually distributed. So a simple idea, basically, yeah, just let's say take top n minus 1, let's say, and remove just like the least important feature from the data set. It already can be a good way to improve your model, or at least make it small. The last but not least, it's a wrapper methods. So what's good about embedding methods, right? We kind of use these, it's already a machine learning model. We kind of optimize the same metric we're interested in, but we have to have access to the model's insights, like, you know, in terms of learned coefficients, in terms of feature importance. Let's say for neural nets, it's not that easy to do, right? You don't have a single vector of coefficients for neural net model. You have actually a lot of coefficients. You have a lot of weights. You don't have a feature importance calculations out of the box for neural net. So basically, you have to do it yourself. And that's what wrapper method's about. You treat the machine learning model as a black box, and you just measure it, you know, the feature performance outside. All you have to have access to is, you know, is a model prediction, for example. So that means you can actually, you know, just like you have a trained model, you just put the features in it, score it, you know, do something with features, for example. I'm gonna show you this a little bit later, and, you know, measure the new score. So it's a more universal technique, but maybe more time consuming. So let's start small, right? Let's start with the recursive feature elimination technique. And the next going to be permutation importance. Well, recursive feature elimination still requires you to have access to the model internals in terms of the features, feature importance or coefficients. And idea is quite simple, right? So basically, what you need to do, you just need to train the model, somehow get the you know, the measurement of the feature importance, you know, in terms of, if in case of linear model, you just need to take the coefficients, and you just remove the feature which has the smallest coefficient. You just drop it, and you repeat this process until a desired number of features is reached. So, well, obviously, because you can explicitly select number of features, that's maybe a good or bad thing about this. That depends on your point of view. I think it's a pro. It's not very expensive algorithm to run. It's a linear model is used. It kind of take feature interaction into account, right? Because you constantly and slowly remove the features one by one. You don't remove like a chunk of features at once, because as soon as you remove the least important feature, the whole distribution of importance, for example, in the forest might change, right? And the next step, you might remove not the same features you would end up removing in the first place. So, well, of course, guess what? Like as soon as we introduce these complex methods, like I said before, you also add additional meta parameter to tune for your model. Like, let's say in this case, you have to find the right number of features to which actually, as a good number of features, which less than total amount of features, but at the same time you have similar performance or performance close to the complete data set. Well, it's actually very, very easy to implement in scikit-learn because scikit-learn does have this implemented for you. So it has a specific transformer called RFE, and you can use it, right away, basically. And again, what's good about that, you can actually you can interchangeably use linear models and random forest, for example. RFE expects the model to have either attribute coefficients, coef underscore, or attribute feature importances underscore. So if they don't, I think they have a wrapper, so you can actually implement it yourself if you want to. So it's quite flexible approach and quite useful. It also, yeah, okay, I can talk about that later. So the permutation importance. That's actually an interesting approach. An idea is quite straightforward, right? So basically what you do, you train your model. Now you have your model, right? You take a validation data set. It's always a good idea to take the data set which model did not see during the training. So it should be out of full data set. If you don't have it, if you have only trained data set, it's good too, but results going to be biased in one way or another. So taking in this validation data set, you just measure performance of your model in this validation data set, and then one by one, you shuffle the feature, a single feature, right? And you put it into the model and measure the difference and measure the score again, right? And now you can actually compare the baseline score on a original unshuffled validation data set with a new score, shuffled data. You're expecting if you shuffle the column, especially important one, right? You kind of expect, because now there is no connection between the shuffled column and a target. You're expecting the score is dropping of the score, and the more significant this drop, the more important feature is for the model. Basically, it gives a really similar results to random forest impurity-based importance. No, but in that particular case, right, this permutation importance is model agnostic because what you need to have, you just need to have access to the model outcomes, basically, and that's it. Usually, if I would like to if I build a neural net model for my tabular data set and I would like to measure the feature importance, that's exactly how I measure it for neural net. It can be, I mean, it's not the fastest one because because you shuffle column, you kind of introduce the how should I put this? Some sort of the noise in your measurement, so you have to repeat this process several times to get the mean score. But it's it's still fairly fast. You also can do column drop variant, but it's gonna be more precise but more time consuming. And again, idea is pretty simple. You train model on a full data set, right? You measure the performance on a validation set. Then after that, you drop one column from the data set, train a new model on it, measure it on the same validation set, drop another column from the data set, and repeat this process as many times as many columns you would like to measure, or you have. Yeah. It's more accurate but more expensive in general because you have to retrain model on every single step. So again, it's model agnostic, which is definitely a pro. It's you can actually base it on a metric of your choice. It can be any metric you wanted. Basically, it's totally fine to have. The why it works and how it works is quite easy to understand. It's very easy to explain to people. Okay, what we just put a garbage instead of the actual value in the column, and model drop score significantly. So it's actually it's very easy to catch up the idea. If we use an independent data set, right? If we use an independent data set out of full data set, the score might actually, if you take the feature importance from your random forest model and this permutation importance score, the ranking of the features might be different because no matter how we train the model, and random forest actually did a great job trying to be unbiased, but it's still going to be biased to the data set it's been trained on. So that includes actually feature importance scores as well. Same problem with highly correlated features. So exactly the same. If you have a highly correlated features, the importance might be actually, the importance score might be split between them. Good news, it's already implemented in scikit-learn. Under the inspection submodule, you have a function permutation importance. It actually asks you to provide the model to use and the data set and how many repeats you would like to do of the shuffling procedure I mentioned before. So basically in this particular case, we have 20 columns, we have 5 repeats. That means we're gonna run the inference of the model given this data set 20 times 5, 100 times. So not very slow, not very fast. It's, it really depends how many features you would like to import. And so basically one of the problem with this approach, actually, if you really have a lot of features to measure, like an example I provided earlier, if you have 500,000 of features to measure permutation importance on, that's going to take a while. And sometimes actually you can do the other way around, which we talk right now. So what we did in the previous approach, we shuffle the feature, right, to measure the performance. What if we shuffle target instead, right? So why not? Idea is fairly simple, right? So we train the model on the data set, given the data set and the target. Now we measure the feature importance, right? That's going to be our null importance, which is original importance, right? After that, we shuffle the target only, and we fit the model on this shuffle target. So basically, we fit the model on a random target because we shuffle it. There's supposed to be no connections between the samples and the target because we shuffle it. And we train a model on this shuffled data set, and we measure the importance of this model on a shuffled target. If the feature importance of particular feature on this shuffled target is higher than the importance on a null feature importance, that's a kind of suspicious feature for us, right? So, if your feature is more important for randomly assigned target, why do you need this feature at all, right? Because it's the good feature is actually really has a connection between the itself and a target. If you shuffle the target, it's going to be it's gonna drop significantly in its importance. If you have a other way around, that's actually a suspicious sign. So what we do basically, we repeat this process n times, and each time we see this this feature importance higher than the null importance, we just assign +1 score to this feature. And if this feature is too often has this +1 assigned, we just basically reject this feature completely. Despite it's being you have to train n+1 model for this approach, sometimes it's actually faster than permutation importance in some cases, especially if you have a ultra-wide data sets, like a lot of features to measure from, if you have a GPU training versus CPU-based inference. Because sometimes, it's I know it's maybe not very good for environment, but basically sometimes it's faster to train on GPU than just measure the inference on CPU. And sometimes it's faster to train the model, 100 times in this particular case and just measure the permutation importance for all the features involved. Same problem. If you have highly correlated features, the model this approach will gonna suffer from them because the model suffers from them. It's kind of black boxish because you still need to have access to feature importance, which you can calculate using the previous approach, but it's going to be quite, complicated schema by the end of the day. So a short implementation of this approach. So we define the model, we get our null importance after we fit the model, and then we just, shuffle our target. We fit the model on shuffle target to get our feature importance. If the feature is, we just, we compare the null importance versus reduced perturbation importance. If we end up having a big number in the result, that's a bad sign. For example, because I run 100 times, if I see these results more than 10 times, I decided to reject these features. It can be quite aggressive, to be honest, right? It's actually, but it is an interesting approach, and I use it a lot, actually. In some cases, it gives me a better subset of the features than I have using any other techniques. So, summary. You cannot have a single technique and that's it. It's by the end of the day, in some cases, you have to try some of them, and some of them can work better than the other. Rule of thumb: by pre-selecting features, by using the feature selection, in some cases, but quite rare, you can actually end up having even better performant model. Just because if your features has a lot of noise, by removing them, these noisy features, you may actually end up giving like a better model which has a better signal to noise ratio. In general case, you actually sacrifice some performance by significantly reducing features needed to train the model. And this sacrifice might be not that big. We're talking about, let's say, AUC from 81 to 80, for example, from 0.81 to 0.80, right? So it can be quite, not significant, but you can reduce the data set size in, order of magnitude in some cases. What's also important to remember about feature selection? Feature selection is a part of machine learning pipeline. And if you would like to measure the performance of your machine learning pipeline correctly, it should be part of a cross-validation or any, out-of-fault validation you have. So you cannot pre-select your features based on a complete data set you have, and then use the pre-selected features to measure model performance in the cross-validation. You will, in that case, you will have a too optimistic measurements of results, because you kind of allow information to leak, because your feature selection method has access to complete data set, to complete train distribution you have, to complete dependencies between features and the target. And it might pre-select features which overall the best. While if you do the same in cross-validation, it's kind of, introduce some noise, because you always have access to only part of information. So always consider your feature selection be a part of your machine learning pipeline in general. And especially if you want to measure, the impact of feature selection on your machine learning pipeline, it has to be cross-validated as a model. Besides, and plus to that, right? That's actually, because some of your feature selection methods do have parameters, you also might consider optimizing them as well, which leads us to cross-validation again. So it's definitely a good idea to have it as a part of cross-validation in general. That's basically all questions all I have for you for today. Thank you.